All right, let's start the notes for section 5.3. We're going to do exponential functions. So up at the top it explains to you how to do an exponential function in your calculator. So I always like to use the caret button. So for example, if you're using your calculator to do this problem, I'm going to just kind of throw my calculator up here so you can see. If I were to do 2 to the 1.4 power, I would press 2 and then the caret button, which is right over here, and then the 1.4 power. And you can see it's about 2.6390. So this first example is just kind of seeing how to use your calculator. So again, this is 2.6390. You can play with the rest of these. I'm just going to throw in the answers here so you can see them. This is what I got each time that I plugged it into the calculator. So you can pause and you can do your own work and plug it into the calculator. So when I plugged in this power, I got 2.6651. Now I rounded. And then when I do this 2 to the root 2, when I round, I get the same thing. Well, that's because the square root of 2 is approximately 1.4142. So you're going to get the same thing. All right, so let's talk about our rules or our laws of exponents. These are from a long time ago. Hopefully you'll remember that if I'm multiplying two expressions with exponents, I add the exponent. So this would be a to the s plus t. If I'm raising a monomial to a power, I multiply the exponents. So that would be to the s times t. If I'm raising a monomial with more than one part, I have to make sure that I bring in that exponent to each one of the parts. 1 to any power is simply 1. If I have a negative exponent, that moves whatever the base is to the bottom of a fraction, so that would be 1 over a to the s power, which is the same thing as 1 over a, that whole thing raised to the s power. And then, of course, anything to the 0 power is defined as 1. Okay, so we're going to do this exploration, but we're not going to spend a whole lot of time on it. We'll do it pretty quickly. Suppose you're given $10 and told that each day you show up to class, the amount you're given doubles. So we're not going to fill in the whole chart, but we'll fill in some of the chart. So you're given $10. So at time 0, you have $10. The next day, you're given twice that, which would be $20. Day 2, you're given twice that, so that would be $40. Day 3, you're given twice that, which is $80. Day 4, you're giving twice that, which is $160. Day 5, you're given $320, and then $640, $1,280, and I can't do that in my head, but you see what's happening. So every time this left column goes up 1, what's happening to the right column? It's being multiplied by 2. So I think we actually just answered this question. As the value of the independent variable, the number of days, increases by 1, what is happening to the value of the dependent variable, or the pay? Well, it's being multiplied by 2. So now it's asking us to create a formula that models that situation. Well, you've got to kind of play with it, but here's the formula that I came up with. So you start with $10, and then we'd multiply that by, since our multiplier is 2, that's going to be our base, and we're going to raise that to the nth power. So for example, if n was 0, if you look back at your chart, when n was 0, 2 to the 0 power is 1, and 1 times 10 is 10, so that fits. If n is 1, 2 to the first power is 2, times 10 is 20. One more, if n is, for example, 3, 2 cubed is 8 times 10 is 80. So you can see that this model that I've written describes what's happening with your ordered pairs that you come up with in the chart from the first page. Okay, so this is an example of what we call an exponential growth function. You've seen where things grow exponentially. You've heard that expression. This is what we're talking about. So an exponential function is a function of the form f of x is equal to c times a to the x power, where a is a positive real number. A is the base or the multiplier. It's got to be positive. Can't be 1, because if you think about it, if you keep multiplying or raising 1 to powers, it's always going to be 1. And of course, c can't be 0, because if c was 0, then the whole exponential function would disappear. The nice thing is the domain of any exponential function will always be all real numbers. Base a, I called it the multiplier. It's called the growth factor in math, but you can think of it as the multiplier. And because f of 0, or whenever you plug 0 in for a, you are always going to get c. C is called the initial value. Okay, so there we are talking about exponential functions and all of their parts. So we did something like this before, but we were just talking about linear functions, if I remember right. So they ask us to determine whether each of the given functions is linear, exponential, or maybe neither one of the two. If it's linear, they want us to find a linear function that models it. And if it's exponential, we're going to find an exponential function. Well, so we're going to do this by looking at the rates of change. Or remember what we call that? We call that the slope. So if I do the slope between this point and this point, so I'm going to do, so let's do this. So y2 minus y1, so negative 4.5 minus negative 3 is negative 1.5, and negative 1 over 0 is negative 1. So the slope using these 2 points is going to be positive 1.5. Let's quickly do these 2 points. Well, negative 3 minus negative 1.5 is negative 1.5 over 0 minus 1 is negative 1. So you're going to get the same thing. Let's skip down to these two just for time's sake. So 0 minus 1.5 is negative 1.5 over 2 minus 3 is negative 1. And again, you get a positive 1.5. So since there's a consistent and constant slope, it can't be exponential. It's got to be linear. And you've just found the slope. So if I want to have a function, I can write it as g of x equals 1.5x. Now, if you quick look at your points, you'll notice that this one is the y-intercept. So it's simply p 1.5x minus 3. So it's linear again because the slope is constant. All right, let's do the next one and see what happens. Well, we're going to do the same thing. So we're going to look at the slope between this point and this point. So 20 minus 16 is 4 over negative 1. So that's going to give me negative 4. Let's go between these two. 16 minus 12 is 4 over 0 minus 1 is negative 1. Again, negative 4. Let's just do the last two to see. So 8 minus 4 is 4 over 2 minus 3 is negative 1. So you can see that that slope that I'm getting when I'm using that average rate of change is always constant. So once again, this means that this is a linear function. And we found the slope, and this is going to be the y-intercept. So it would be h of x is equal to negative 4x plus 16. So it's probably no surprise what's going to happen here, but let's do it anyway. So if we go ahead and if we do, again, that average rate of change, 2 minus 3 is negative 1 over negative 1 minus 0 is negative 1. So that's going to be positive 1. If I do these two, 3 minus 4.5 is going to be negative 1.5 over 0 minus 1 is negative 1. So that's going to be 1.5. So you can see it's not linear. If I do these two and subtract, 4.5 minus 6.75 is negative 2.25. And again, 1 minus 2 is negative 1. So that gives me 2.25. And I'm running out of room, but I'm going to show you these. If I subtract 6.75 minus the 10 and an eighth, you get negative 3.375. And that's over, again, 2 minus 3 is negative 1, so you get 3.375. So you can see it's not linear. It's going to be exponential. So we have to come up with an exponential function. Well, we have to figure out what our growth factor is, or our multiplier. And if you look from here to here, it's multiplied by 1.5. If you do the math, multiply 1.5 and 1.5, you're going to get 2.25. Multiply 2.25 and 1.5, and you're going to get this last number, 3.375. So your multiplier is 1.5. So that is your A. We still need the C. Well, if we look at this point, at x equals 0, it is 3. So that means that there's going to be 3 there. So there's that function. So let's look at some properties. Now remember, you can stop this video at any time.